Hello student, today I will discuss about some question of stereochemistry. First question is define specific rotation for an optically active molecule. See, this is the equation for specific rotation. So specific rotation is equal to rotation observed when a plane polarized light is passed through a 1 decimeter solution having concentration of 1 gram per ml. So L should be 1 and C should be 1. Then specific rotation will be equal to rotation observed. Now a compound that rotates a plane polarized light to the this is plane polarized light to the right hand side or clockwise means in this way is termed as dextrorotatory and represented by small d or plus sign. And a compound that rotates a plane polarized light to the left hand side or anti-clockwise means in this way is termed as levorotatory and represented by small l or minus sign. Now second question is, what is the necessary and sufficient condition for a molecule to be optically active? See, there are three types of symmetry element: plane of symmetry, center of symmetry and n-fold axis of symmetry. I will discuss this later. If you have three types, either one type of symmetry in your complex, then that molecule will be achiral. And if these symmetries are absent, if these symmetries are absent, then that molecule will be called chiral molecule. And if you have chiral molecule, that molecule will be optically active. So condition will be this: any of these three elements of symmetry should be absent, then the molecule will be called chiral molecule. And if you have chiral molecule, that molecule will be optically active. Now next question is, Allene compound does not have a chiral center, still it shows optical activity. Comment. This is Allene complex. See, these two hydrogen atoms are in the plane of paper, and this hydrogen atom is above the plane and this hydrogen atom is below the plane, and this carbon is sp2 hybridized, this carbon is sp hybridized, and this carbon is sp2 hybridized. Now see the orbital picture of Allene. See, this is sp2 hybridized carbon, so there will be three sp2 hybridized orbital for this carbon. See, this carbon, one sp2 hybridized orbital, another and another. See, this carbon is sp hybridized, so there should be 1 and 2 sp hybridized orbital will be there. See, for central carbon 1 sp, 1 sp, and this carbon is sp2, so there should be 3 sp2 hybridized orbital, 1, 2 and 3. Now sp2 hybridized orbital of this carbon will overlap with sp hybridized orbital of this carbon, and sp hybrid orbital of this carbon will overlap with sp2 hybridized orbital of this carbon, and 1s orbital of hydrogen will overlap with sp2 hybridized orbital of this carbon, and 1s orbital of hydrogen will overlap with sp2 hybridized orbital of this carbon. Here also same case, this is also same case. Now carbon will have tetravalency, so 1, 2, 3 bond done. Another there should be a unhybridized p orbital. This is unhybridized p orbital, and these three are hybridized sp2 orbital. Okay, so this will having one unhybridized p orbital. This carbon will having two unhybridized p orbital because there are two hybridized orbital sp. So carbon should have tetravalency. So 1, 2, 3, 4. So this carbon will have two unhybridized p orbital, and this carbon is sp2 means 1, 2, 3 done. Then there should be one unhybridized p orbital. Now this unhybridized p orbital will overlap with this unhybridized p orbital of this carbon, and this unhybridized p orbital of this carbon will overlap with unhybridized p orbital of this carbon. This is one p orbital and this is another p orbital. Now See, optical activity in Allene complex are due to molecular dissymmetry. And the reason for the dissymmetry is that the groups hydrogen and hydrogen at one end of the system lie in a plane. See, these hydrogen are in a plane at right angle to those of the other end. And other end, see, these hydrogen atoms are at right angle with this hydrogen because this hydrogen is above the planes, mean in this way, and this hydrogen is in the plane. Now see, angle between them should be 90 degree, and here also this hydrogen is below the plane and this hydrogen is in the plane, so there should be angle of 90 degree. This can be explained from its orbital picture as shown above. This is the orbital picture, and here central carbon atom has two mutually perpendicular p orbital. See, one p orbital and another p orbital. These p orbital are mutually perpendicular, means if this p orbital present in this way, then this p orbital should be present in this way. In this way, there must be an angle between these two unhybridized p orbital. There should be angle of 90 degree. The substituent at one end are in a plane. See, these substituent are in a plane which is perpendicular to that of the substituent at the other end, and this should be perpendicular to this one, means there should be angle of 90 degree. Thank you.